All right, so what is Laplace transform? So Laplace transform is a very interesting thing. Its input is a function, right? So suppose that we have a function whose domain is the interval from 0 to infinity. So then we can compute the Laplace transform of this function, and the output is going to be another function, right? So if the input is a function of t, then the output is going to be a function of s, whose value is given according to this formula. A problem for you to think about, please pause my lecture and try to think what this Laplace transform is mathematically. And the answer is, wait for it. The answer is, so notice that if we try to find Laplace transform of, say, f of t plus g of t, and this is going to be the integral from 0 to infinity of e to the minus st f of t plus g of t dt, which is really the Laplace transform of f of t plus the Laplace transform of g of t. Right? And at the same time, you can, if you multiply f of t by a constant, so L of, so let's multiply f of t by some constant, say, I don't know, lambda is a constant, lambda f of t, and this is going to be the integral from 0 to infinity of e to the minus st lambda f of t dt, but then lambda can be taken out, and this is nothing else but lambda times L of f of t. Right, so which means that Laplace transform is actually a linear transformation of infinitely dimensional vector spaces. Right, so the Laplace transform is a linear transformation from the space of all functions to the space of all functions. So that's the answer. Okay, let me go through a couple of examples of the Laplace transform. There are 4 examples here, but I'll do 2 of them, and I suggest that you try to do the other 2. Okay. So how can we calculate the Laplace transform of, say, e to the minus 2t? And so the Laplace transform of e to the minus 2t, it should be a function of s, right? And it is defined by the following formula: 0 to infinity. So first I write e to the minus st times my f of t. My f of t is e to the minus 2t. So that e to the minus 2t dt. Well, but this is the integral from 0 to infinity of e to the minus s plus 2t dt. So now we can find the antiderivative, and the antiderivative of e to the minus s plus 2t is really minus e to the minus s plus 2. Oh, sorry. S plus 2t over s plus 2. That's the antiderivative, and the integral should be from 0 to infinity, so we have to take this change from 0 to infinity. Yeah, but here we have an interesting thing. So notice that if s plus 2 is a positive number, then the exponent is negative, and the limit of e to the minus s plus 2t as t goes to infinity is 0. Then everything is all right. But if s plus 2 is non-positive, then the limit, e to the minus s plus 2t, when t goes to infinity, it doesn't approach 0, and it either approaches infinity or it just remains to be to be 0. But in other case, the integral diverges. Right? So it means that this is true only if s plus 2 is positive, so which means that s is bigger than minus 2. And we are going to have the following thing. So the minus the limit of e to the minus s plus 2t as t goes to infinity is going to be 0. So 0s plus 2. Minus and minus gives us plus, so plus. If t is 0, then e to the minus s plus 2t is 1. So 1 over s plus 2. So which means, let me write it here. Right, so this whole thing is going to be undefined if s is less than or equal to minus 2, and 1 over s plus 2 if s is bigger than minus 2. Yeah, that's the answer. Right, so in other words, the Laplace transform is going to be another function. Now it is a function of s, and its domain is actually different than the domain of the original function, right? Well, but s and t are they are not related to each other. So here s belongs to the interval from minus 2 to infinity. Right? Okay, I hope it's clear. So let me maybe just to have one more example is to do the cosine. Okay. So let me do the cosine. So suppose that I want to do a Laplace transform of cosine t. Then again, by the definition, I need to write the integral from 0 to infinity of e to the minus st cos t dt. So the antiderivative of e to the minus st cosine t, I know it because I looked it up on Wolfram Alpha. So this is going to be e to the minus st times sine t minus s cosine t over s squared plus 1. So that's the antiderivative of e to the minus st times cosine t, and we have to take the change from 0 to infinity. So now notice that if s is a positive number, then the limit at infinity exists and is 0, and we are fine. But if s is a negative number, then e to the minus st would be growing as t goes to infinity, and therefore this integral diverges. So meaning that there is no value at all, right? So this is only defined if s is positive. Okay, but if s is positive, then the value at infinity is 0. So the limit of e to the minus st as t goes to infinity is 0. So we need to subtract the value at 0. And when t is 0, e to the minus st is 1, sine 0 is 0, so minus s cosine 0 is 1, so we have minus s over s squared plus 1, and we have to subtract it from 0, so which means it's really s over s squared plus 1. Right? But again, this only works if s is positive, which means that the full answer is actually the piecewise defined function undefined if s is positive, and this s over s squared plus 1 if s is undefined if s is non-positive, less than or equal to 0, and s over s squared plus 1 if s is positive. And I suggest that you try to figure out the other two. And here is the answer. All right. Now, definition. I'm not sure if it's the definition. So let me clarify this a little bit, right? So if there exist constants that kind of bound the growth of the function f of t as t goes to infinity, right? So this condition, essentially, it means that this condition, essentially it means that the function f doesn't grow faster than an exponential function. But let me explain what I mean. Suppose that f satisfies this property, right? Then the Laplace transform of f is going to be like integral from 0 to infinity e to the minus st f of t dt. Well, and if we want to estimate it from above, so let me write the absolute value. So the estimate from above is going to be less than or equal than from 0 to infinity e to the minus st, and I'm going to apply the estimate for f of t, right? So it's going to be times k e to the at dt, which is the integral from 0 to infinity. So k can be factored out, and what is inside integration is e to the power minus s minus a t dt. Right? And this integral is well defined as long as s is bigger than a. Right? So let me write it down. That not well defined. The integral converges. Right? So this is an improper integral, so it converges if s is bigger than a. Because if s is bigger than a, then s minus a is still positive, and we have e to the power minus positive number t, so exponential function with a negative exponent. Yeah, and at infinity it's going to approach 0, and the whole integral is going to converge. And the fact that the integral converges, as we saw in the examples, it means that the Laplace transform is well defined. Right? So in other words, it means that we can always calculate the Laplace transform of any polynomial or trigonometric functions or exponential functions, so anything of the sort that does not grow too fast is okay. But so if, say, on the contrary, imagine that you want to calculate the Laplace transform of e to the power t squared, 0 to infinity, e to the minus st times e to the t squared dt. Can you do that? And then the problem is that you'll have the integral from 0 to infinity of e to the power t squared minus st dt. And no matter how large s is, eventually when t is sufficiently large, t squared minus st is going to be positive, and this thing is going to grow faster than an exponential function, and the integral diverges. right? So since this integral diverges, it means that the Laplace transform just is undefined for any value of s, right? So there doesn't exist a Laplace transform of this function. And a very good problem, but that's a hard one, but try to maybe figure it out. That if Laplace transform is a linear transformation from one vector space to another vector space, then what are the vector spaces? So the crucial property of a Laplace transform is that the Laplace transform of the first derivative can be the Laplace transform. In a way, it transforms differentiation to multiplication, but with s. That's what it says. And a good problem is to prove this theorem. That's an easier problem than the previous one. And again, I suggest that you just pause the lecture and try to figure it out by yourself. And here is how you can do it. Right, so suppose that we want to calculate the Laplace transform of f prime of t. And this is by definition the integral from 0 to infinity e to the minus st f prime of t dt. And now we're going to do something very clever. We're going to integrate this by parts. Right? And I hope you know that when we integrate by parts, then we need to take the antiderivatives of one of these two functions and the derivative of the other one. Right? So what we are going to do, we are going to take antiderivative of f prime and the derivative of e to the minus st. So the answer is going to be e to the minus st times f of t, change from 0 to infinity, minus the integral from 0 to infinity of what? We need to take the derivative of e to the minus st, which is minus s e to the minus st, times f of t dt. Right? Which is in turn the change of e to the minus st from 0 to infinity. So what is it? At infinity, since f of t is supposed to be a function that doesn't grow too quickly, it means that at infinity the limit of e to the minus st times f of t is going to be 0. Right? But what are we going to have at 0? So at 0, we're going to have e to the minus s times 0 is just 1 times f of 0. So this is minus f of 0. And the second term, so we have minus and minus is going to give us plus. That's one thing. So another thing, so notice that the integration here is with respect to t. So which means that s can be taken out. But now this part is just the Laplace transform of f. So this is plus s times the Laplace transform of f of t. Right? So which is exactly what we are supposed to prove. Right? So that's the first statement. And the second statement is, notice that we just need to apply the first statement 2 times, and then we'll get the second statement. And in a similar manner, you can calculate the Laplace transform of f, third derivative, fourth derivative, and so on. right? So